the problem you were given was basically to show that if you have a constant force Fnet acting through displacement delta x, then the quantity 1/2 mv squared has a change that's equal to the product of Fnet and delta x. And we phrased that problem, or I phrased that problem as if something starts from rest and a net mass m starts from rest and net force Fnet acts on that mass through displacement delta x, then the quantity 1/2 mv squared will change by the quantity Fnet delta x. And then the second question extended that to even if you don't start from rest. You start from any velocity and apply net force to the mass m through displacement delta x, then again 1/2 mv squared has the same change, Fnet delta x. And it doesn't matter what velocity you start at. Okay, well, with the first problem, people didn't get very far trying to do stuff with symbols and not sure what to do with it. And I was a little surprised at that because, of course, it's just a kinematic situation. At least once you realize that the acceleration is Fnet divided by mass, which is something that I've seen people using quite adeptly in the homework. So I didn't really expect a problem with that part of it, but it's challenging to work out. So I did ask people to, well, make up some numbers. Don't use ones, don't use zeros, use different numbers for different quantities, and work it out and see what you get. And it was still, people ran into difficulties. Also, people were trying to use things they learned in dynamics about work and energy because they did recognize that this is a situation where you talk about work and energy. At least they knew that Fnet delta x was the amount of work. Didn't see a lot of evidence, but there, it doesn't mean it wasn't there. That people knew about the work kinetic energy theorem, but after all, that's what we're trying to derive in this class. So you might not have derived it in that class, but you probably have used it some. Well, anyhow, one way or another, people made the connection with work, but you want to forget that. We see why we define this as work. We see why this is work. Okay. So if you know V0, acceleration, and delta x, well, that's just a kinematic situation. If you know and acceleration, we have a constant net force. It's supposed to be constant. We know acceleration is constant. So we could use the kinematic equations if we wanted to. People didn't seem to be as familiar as I expected with the kinematic equations, but I expect that to change pretty easily. And perhaps because you've been doing your homework with the equations in front of you and not really thinking about the equations or remembering them. You're going to have to know them. But we haven't talked a lot about the kinematic equations because we've been using the more general approach where we use the second integral of a constant acceleration and use initial conditions and so forth. But you really want to be able to use those equations. And the key to the kinematic equations is basically there are 5 quantities. You got V0, initial velocity, which the book calls V0. You have Vf, the final velocity at the end of some interval, or the velocity V at time t. You have the change in time or the clock time t. You have the displacement, the delta x. And actually what you probably have is you have x0 and x, so x minus x0, your delta x and all that stuff. You have a fairly simple scheme in the kinematic equations. So this feeds directly into the scheme because you know this, this, and this. You can use the kinematic equations to solve for velocities and so forth. Okay. So you could use the kinematic equation. You could write x of t, the x of t function, the quadratic x of t function. Let's put the word quadratic. And of course you should never forget where that function comes from. Integrate the acceleration once, you get a V0 plus AT. Integrate that again, you get this. So constant acceleration implies this. Also then, the kinematic equations, final velocities, initial velocity times t plus 1/2 AT squared. Your delta x, which is your x minus x0, is the average of initial and final velocities multiplied by delta t. and so forth. Whichever way these are expressed, whichever way you prefer to see these expressed, you can use these equations. Or you could use a graph. You got a graph on a velocity versus time, a set of coordinate axes. You're going to have a change in time, a delta t between two events. First event occurs when velocity is v0, second vf. The slope of the line segment between this point and this point is going to be the acceleration, and the area under the curve is going to be your displacement delta x. You should be able to reason this way, or this way. Okay, well, we can go up here using the formulation that we've, now actually I went to the kinematic equation, but it's completely equivalent to this formulation. Matter of fact, I'm not sure which one I was doing. If we go to this, which is equivalent to one of your kinematic equations, x of t minus x naught equals v naught t plus 1/2 at squared. Okay? And it follows from this that v of t is v naught plus at. Of course, this was a step you went through when you integrated the acceleration. You had to integrate this to get this. These two equations go hand in hand, along with the fact that acceleration is constant. Okay. What information are we given? We're given the net force and the mass, and the displacement and the initial velocity. In the first problem, the initial velocity was said to be 0. In the second problem, it was said not to be 0. So let's go to the more general problem, but it doesn't really matter which we're doing. We're going to have a v0, whether it's 0 or not. Okay, from Fnet and m, clearly you can get A by Newton's second law. So you have this dynamic problem where you have a net force, a mass, and some other information. And it immediately becomes a kinematic problem where you just have an acceleration that you put into this, a delta x that you can put into this, and a v0 that you can put into this, allowing you to do any variety of things. From these two equations, we can derive this equation, one of the kinematic equations. And this is the route that we actually chose to use in our solution. So this is a kinematic equation. Vf squared equals v naught squared plus 2a delta x. Okay, well, if we replace a by Fnet over m, what do we get? We get, well, the 2a delta x becomes 2 Fnet over m times delta x. That Fnet isn't written very well, and it still isn't written very well, but at least the t is crossed. Okay. Now, what are we trying to do? We're trying to relate Fnet delta x to a change in 1/2 mv squared, which you probably recognize as kinetic energy, but that should make no difference. It doesn't make any difference in solving this problem. You got to get it from this process. Okay, well, it took me a while to drag this out of people, not too long. Do you see anything about 1/2 mv squared in this equation? It's there actually, but you probably don't see it. The one thing that you probably do see is Fnet delta x, and I circled it. There's your Fnet delta x. Okay, well, it would make sense then to solve this equation for Fnet delta x. First step in solving for Fnet delta x would be to subtract v naught squared from both sides. Now, switching sides, we got 2 over m times Fnet delta x, vf squared minus v naught squared on the other side. So we finish solving for Fnet delta x. We multiply through by m over 2. Okay, having done that, we get this. Now, it took a long time to get from here to here when we did it in class. So I digressed over to the idea, okay, if v naught is 0, then you don't have this. And if v naught is 0, what do you get? You get Fnet delta x is m over 2 times vf squared. How could that be related to anything that looks like this? Well, m over 2 times vf squared is 1/2 m vf squared. That's like a 1/2 mv squared. Now you got a subscript f on there, but that's okay for the moment. You see now that we have something like Fnet delta x equals 1/2 m Vf squared. That's a whole lot like what we have here, except we have a delta. How do you reconcile that? Well, if the initial value of 1/2 mv squared was 0, which it is if we assume that v naught is 0, which we had to do to get this form, then the final value of 1/2 mv squared has to be the change in the value. Okay, if you start from 0, then whatever you end up with, that is the change, and you want to think about that. Okay, so we've actually kind of now proven this for the case where v naught equals 0 without even necessarily intending to. It just kind of fell out off to the side here. Let's go back to where we are here. What can you do here that's going to give you something that illuminates this? Well, why don't we distribute the multiplication by m over 2? You get m over 2 vf squared minus m over 2 v naught squared. So we did this, and still people were unsure where to go from there because, you know, in the booming, buzzing confusion of all this, we don't necessarily see this and how it relates. But obviously, we had an m over 2 vf squared here. We changed that to 1/2 m vf squared. And now it was in this form, so we really want to do the same here. So we get 1/2 m vf squared minus 1/2 m v naught squared. So that's what we have here. Okay, now, what is this? Vf being the value at the end of this delta x interval where the force Fnet applied to mass m from some initial velocity. 1/2 m vf squared will be our final value of 1/2 mv squared. So final value of 1/2 mv squared is 1/2 m times final value of v squared. Initial value is of 1/2 mv squared is 1/2 m times the initial v squared. This then is the change in 1/2 mv squared. So our Fnet delta x was equal to the change in 1/2 mv squared. And we have proven it. Took way longer than it should have to do this, which just means that not that people are deficient or so forth, because my current class doesn't have any unusual deficiencies. Of course, everybody has deficiencies from whatever they happen to have learned previously. It just means that you need to look at this until it makes perfect sense, because this is the basis for our whole analysis of energy. Again, the lesson is constant net force acting through displacement delta x changes the quantity 1/2 mv squared by the product Fnet delta x. And this is called work. This thing's called energy, so this is change, kinetic energy. This is the change in kinetic energy.